Now we're going to look at an example of a force stamp vibration question. In this question we're looking at a rocker arm of length AB. We're given a number of known values and we're asked to work out the value of C, or the damping coefficient. Now I've started out this question by drawing a free-body diagram, which you can see here. So I've started out this question by drawing a free-body diagram with the sinusoidal force at A over here, and then I've got two forces up this end. One of them will be the component from the spring and the other will be the component from the viscous damper. So we need to look at the force component that's going to be provided by the spring. Now, as we know, force due to a spring is K, or the spring stiffness, times the extension. Now in this case our extension will be this length here when we're looking at displacing this rocker arm an angle of theta. So the solid line represents the rocker arm at its equilibrium, and then we're displacing this rocker arm an angle of theta about the pivot here, so it takes up this dotted line position here. Now this extension is equal to OB, or the length here, times the sine of the angle theta. So in this case the force provided by the spring is going to be equal to K, spring stiffness, times OB sine theta. Now with this example we're assuming that we're going to be displacing the rocker arm by a small angle, and that means we can use the small angle assumption. This says that the sine of theta is going to be equal to theta. So we can replace sine theta here with just theta. The force provided by the viscous damper is going to be equal to C theta dot, where C is a damping coefficient and theta dot is the angular velocity. Now we're also going to need to times this by the distance from which it acts from the pivot, which is AB. So we're going to have C theta dot OB. So now we've got all our forces marked on our free body diagram, we can start looking at producing an equation of motion for this. Now, as with any dynamics problem, this is going to be looking at the sum of the forces, and this is going to be equal to MA. As this is a rotational question, we're not going to be looking at F equals MA, but instead the rotational equivalent, which is I theta double dot, or the inertia times the angular acceleration. So next we need to sum the forces that are going to be on the right hand side of this equation. Now to do this we need to assume a positive direction of rotation with our free body diagram, and you can put this anyway, but I'm going to assume it's in the clockwise direction for this. So we'll start by looking at the forces provided by the spring and the viscous damper first. Now you can see these forces are going to produce a moment about the point O here, and that moment is going to be equal to OB times K OB theta for the spring component, and OB multiplied by C theta dot OB. Now these forces are both going to act in the opposite way to our assumed positive direction, so these are both going to be minus elements. So as I say, we're going to have OB times K OB theta, which is also equal to OB squared K theta, and then again minus OB squared C theta dot. Now looking at our sinusoidal force over here, we can see this is going to rotate the rocker arm in the positive direction, which is clockwise, and this force is going to act at a distance OA from the centre of rotation. So this is going to be a positive, so plus F naught sine omega t times OA. So I'm just going to rewrite this to neaten it up a bit with these two components on the left hand side. So these are going to go to pluses, plus OB squared C theta dot, and that's all going to be equal to F naught sine omega t times OA. Now to progress with this question we need to assume a particular solution, And our particular solution for this question is going to be that theta, or the angular displacement, is equal to x, which is the amplitude of vibration, sine omega t minus phi. Phi is the phase angle here, w is the frequency, and t is time. Now you can see that we don't just have theta elements in our equation of motion over here, we also have theta dot and theta double dot. So in order to substitute our particular solution into our equation of motion, we're going to have to come up with the first differentiation of this particular solution and also the second. So the first differential of this particular solution is going to be equal to omega x cos omega t minus phi. The second differential is going to be equal to minus, as this cos is going to change into a minus sign. It's going to be omega squared x sine omega t minus phi. Now we can substitute these values for theta, theta dot and theta double dot into our equation of motion over here. So what we're going to have is minus omega squared I x sine omega t minus phi plus ob squared, that's all squared, c omega x cos omega t minus phi plus ob squared k x sine omega t minus phi, and that's equal to OA f naught sine omega t. Now we're next going to produce a phasor diagram, also known as a vector polygon. So I'm going to start by drawing a set of axes here, and each one of these components in our equation of motion is going to be equal to a phasor, where the argument is either going to be the sine or cosine component of each, and the magnitude is going to be equal to the coefficient of that argument. So in this case it will be minus omega squared ix. Now I'm going to start by drawing the phasor that relates to the force provided by the spring, which is this one here. So I'm going to approximate the angle to look something like this, and then put the magnitude of that is equal to ob squared kx. Now I'm next going to mark on the phasor for this component here. Now, if this was from the origin, this phasor would look something like this. But for us to actually produce a vector polygon, we're going to translate this over here, and this is going to be a right angle to the last phasor that we drew in. And the magnitude of this one is equal to ob squared c omega x. As you can see, I'm just taking out this component from here. I'm next going to mark on this phasor here, and now this is going to be in the negative direction, coming back towards the origin, so it's going to look something like this. And then finally we've got our sinusoidal force, which is going to close the vector polygon here, and this has a magnitude of OA f naught. Now to look at finding c, we can produce an equation which relates all four of these phasors. And to do this we're going to use simple Pythagoras theorem, and this is going to state that this length squared is equal to the sum of this length squared plus this length here squared. So I'm just going to write that out, which is OA f naught squared is equal to this length here, and this length is going to be equal to ob squared kx here minus this length here, which is minus w squared ix. So this is going to turn to a plus, and we're going to end up with ob squared kx plus w squared ix all squared, and then this length here is simply this length. So I'm going to plus ob squared c omega x all squared. Now we're going to need to start substituting some values in here, and I'm just going to make a note of the values that were actually given in the question. So we're given that F0 is equal to 10 newtons. The vibrational amplitude, or X, is equal to 500 microradians. Omega is equal to 80 Hertz, which in radians is just multiplied by 2 pi to get 160 pi radians per second. Our value of K is equal to 1000 newtons per meter. And now looking at this equation down here, you can see that the only thing that we have missing now, other than C, is our value of I, or the inertia. So we need to work that out before we can move on. Our value of I about the centre of rotation is going to be equal to the inertia of the rod, and we know that the inertia of a rod is equal to ml squared over 12. Now you'll notice that the centre of rotation doesn't actually fall on the same point as the centre of mass of the rocker. There's actually a distance here, which I'm going to call y, between the two. Now this means that we're going to have to use parallel axis theorem, which says that the inertia of the rod about the centre of rotation is equal to the inertia of the rod plus the mass times the distance between the centre of rotation and the centre of mass, or my squared. Now y in this case is equal to L1, and the value of L1 that we're given in the question is equal to 0.05 meters. We're given that the length of the rod is equal to 0.3 meters, and we're also given that the mass of the rod is equal to 0.5 kilograms. So substituting these values for m, y and L into this equation here, we should get that I0 is equal to 5 times 10 to the minus 3 kilograms meter squared. Now substituting our known values into this equation here, we should get that 1 is equal to 0.374 plus c squared times 1.01 times 10 to the minus 4. And from this we should be able to work out that c is equal to 78.7 Newton seconds per meter.